Welcome everyone. The today's session of this MCMT subject, I would like to discuss regarding the different kinds of materials utilized for the machining condition as the tools and the internal characteristics of the tool materials which will be utilized for different working processes. Then to the point of this tool materials, as far as from the past history is considered, in the case of 1910, the HSS material, high-speed steel material, came into the existence to a minimum level of utilization. That too, for process commencement over the lathe machine for turning operation on the mild steel materials. And later on, 1923, the brazed materials such as carbide materials, which are having a bit incremental with respect to its strength and stiffness, that it can be removed the material for a parameters of cutting maintained with respect to a speed of 60 meters per minute. And later on, carbide conditions, those materials has been increased in the utilization for the MRR condition of 80 meters per minute. So the stiffness and the strength related to the material by carburizing addition of the carbon to the material in its composition varies the mechanical properties of the material, which is furtherly increased regarding this coated carbide materials that are machined to a range of 250 meters per minute. As per the ceramic materials for coating over these materials utilized as the tools for removing the material, excess material over the part in the form of a chips. The maximum of 750 meters per minute as considered in the 2000 series. Presently, 2008 has been furtherly utilized this CBN tools, carbon boron nitride, CBN, carbon boron nitride tools, which can be machined to a range of 1150 meters per minute. And later on in 2016, PCBN tools came into the existence that we'll be calling as polyvinylidene carbon boron nitride tools. So these are also the materials plays a major role for working acetation at a high speed and depth of cuts can be processed the MRR rate at 1400 meters per minute. So coming to the utilization point of view, for the machining operation at a heavy range, the tools plays a major role in order to get a definite shapes for the materials without disturbing its internal structures, without deviating its surface finishing levels, and producing the required dimensional accuracies with a greater accuracies and great efficiency over those materials. The main phenomena is that the hardness containing tools. So the main need or necessary cutting tool materials or as this follows, which will be utilized for meeting the high productivity ratio with less economical offense and enabling for the effective and efficient machining process for the exotic materials, getting the high precision values in the case of dimensions. That too regarding the micro level and even the nano level of being accessed with the help of our microscopic techniques and even rational in operational procedures such as CNC machineries, etc. So the major constraint here it is has to achieve the good surface finish upon machining process by satisfying the input parameters or input conditions given in the form of a program need to be achieved the perfect dimensions and even the high surface finishing over the object. The representation overall the chronological development of these cutting tools listed based upon the decade level of estimation and improvement over the decade. The major need for the automobile sector came into the existence for getting the parts to the required dimensions with the help of this HSS tool material, which is a combination of chromium 4%, vanadium 18%, vanadium 1%, carbon 0.7%, and that too towards 1920. The percentage levels here just varies with respect to the HSS metal, which we are replacing for work bond above 1. That comprises the composition levels of the tool: vanadium 2 to 4% nominally, cobalt 5 to 12% in palladium and chromium. For the aircraft applications, for aircraft parts preparation, the tools such as carbide coating for the steels will be utilized, as this carbide gives the good strength for the steels over the that these can resist to an high temperature levels. So nominally we used to observe during the machining process temperatures will be used to produce, and based on that due to the frictional forces high stresses will be developed, thermal stresses, and indeed to compete with respect to that stresses in the case of hard machining process without utilizing the lubrication sector. Nominally equivalent dimensions will be achieved by these conditions, that is sinter carbide for cast iron, even the carbide for steels, and proceeding furtherly for chemical and petrochemical nuclear applications in 1950s, HSS material with respect to a composition of vanadium, molybdenum, cobalt, carbon, and the ceramics and sintered diamond composition plays a major role over here. The jet engines and space programs in 1960s, ceramics and ceramides plays a major role for machining for the parts to be manufactured. Like that in 70s, coated carbides, 80s, carbon boron nitride coated with respect to HSS or the HSS material. And presently PCBN, which is playing a major role within high strengthened materials, diamond coated carbides will be released for machining over the different parts for achieving the better dimensional accuracies. This is the chronological development of the tool materials from the 1900 to 1990. Until now, this carbon boron nitride tools with respect to addition of polymers towards it, polycrystalline or cubic boron nitride materials playing a major role in the present day world for finishing, high surface finishing achievement during the machining process, either of the turning, drilling, milling, etc. processes. Coming to the characteristics of these cutting tools, hardness that plays a major role, the primitive part, because the tool it should be very much hard to compete or remove the material by maintaining the conditions over it, the speed, feel, and depth of cut. If there is higher hardness to the tool, it's very much easy to penetrate through the material, and the performance over the work part will be done in a perfect ratio without affecting its finishing levels. Next point is the hardness. Hardness is it's the ability of the cutting tool which maintain its hardness and strength at elevated temperatures, which are nominally used at high cutting speeds for rationalizing the productivity of the materials within the industry, and even a strict condition, that is without going to the plastic deformation, entire the process need to be commenced indeed to retain its original shape and sharpness. So the tool tip upon machining process, even though the maximum stresses which are being produced over it should not be retained to its original, or deformations that too exceeding towards the Hooke's law concept. So as we all know that the Hooke's law, within the elasticity limit, stresses are directly proportional to the strains. Hence, plastic deformation and some permanent deformations that are being produced over the materials upon machining conditions towards the tool. That should not be commensurate. Coming to the toughness point, the tool should have the enough toughness to withstand due to the impact loads and the fluctuations which are being created by the work part of holding device, nothing but the jigs and fixtures, and towards the arbor. If there isn't something deviations has been commenced with the holding of this work part, it leads to some minor defects, such as more amount of material need to be elevated due to the chip contact that will get in assist with respect to the tool and remove the material to an high ratio. And most probably we used to observe this MRR at an high thickness elevations in the case of this milling process. Coming to the whir resistance, the tool chip and work interface, chip work interface, which are exposed to severe conditions and adhere, the abrasive work is very much commonly elevated at the agitation of this repeatedly applying load conditions. So nominally, the process it continues to a maximum levels. That material has to be removed continuously to a particular range. Hence, the repeated load will be applied over the materials for remove the material MRR, such as excess material. We should say the excess material for getting the better finishing levels. But here the whir resistance. So whir resistance, about the repeated loading, the material or tool should be able to withstand up to a particular stresses and strain levels. Nominally up to a particular stress levels. And even the whir resistance means the attainment of acceptable tool life before tool need to be replaced. So maximum yield point containing loads are being observed within the material, and hence that's the step before to the rupture point, and hence getting the access to replace the tool. The characteristic of low friction, the coefficient of friction between this tool and chip should be very much low, as this would lower the whir rates and allow the better chip flow process. As the frictional resistance has been increased, or the friction between this work part and the tool is very much low, automatically a lower whir rates will be getting formed. The deformative sensations will be very much low and leads to better machining conditions. Coming to the point of this chemical stability and inertness, most probably it's being avoided or minimized for any adverse reactions or adhesions because of the tool chip diffusion contribute to the tool wear. So the characteristic such as the chemical stability will be getting avoided over the material with respect to the material particularly. Coming to the point of the thermal characteristics, Hence, upon machining process, by mating with respect to this tool and the work part interface, high amount of thermal stresses or conductivity leads to a dissipation of the heat that usually become very much high at a peak level, which will cause the life of the tool, hence leads to decrementing of the lifetime with respect to the tool material. Considering these primary cutting tool materials, carbon and medium alloy steels, when you have been utilized as a tool materials, as you have been chronological schematical diagram we have seen, it is an oldest method of utilizing this tool materials, something around this 1900s series. They have followed a simple term, that is high carbon steel, which is having a composition of 0.9 to 1.3 percentage of carbon for the composition of the material. It is inexpensive and used for shaped conditions by sharpening, and moreover, it is limited to low cutting speed operations. So RPM, nothing but speed, should be confined to a particular extent only. Coming to this HSS material 1905 series, the alloying of the additive materials over these HSS materials such as manganese, chromium, vanadium, molybdenum, which are the additive materials that provide the strength to the existing material, that makes this material to resist with respect to the heat conditions or heat confined zones. For this, there are two types. First one is the tungsten HSS, denoted with respect to the letter T, and second it is a molybdenum HSS, which is denoted with respect to the M. The basic composition related to this HSS for utilized for especially the hot hardness, that is 18% of the palladium, 4% of chromium for deformation of the resistance, 1% of the vanadium for one resistance, including for the tool, and getting for the stiffness 0.7 percentage, and remaining percentage will be utilized for the ferrous. Will be in the olden days, this HSS 1905 has been utilized, and still only for the especially for the turning operations or the lathe machines, in minimum speed levels, feed levels, and depth of cut. This material is still utilizing for machining processes. That will maintain the tool geometry and mechanics of chips deformations, very much complex. Nominally, we used to utilize that twisted drills, reamers, gear shaping cutters, even from the tools, broaches, etc. These are the processes at which these HSS metal will be used as a tool. And brittle tools such as carbides, ceramics, etc. These are not preferred because the shock loadings leads to an fractures over the materials, because this HSS is having the high strength and it's less brittle, or brittle materials will not be commenced or suitable for machining by the HSS2. The small scale industries, it cannot be afforded because steel is very much costly. and nominally we'll be saying it's some high economical. The old and low powered small machines cannot accept this high speed and feed rates, as we have already discussed that this tool is confined only to the normal feed speed and depth of cut, but not in maximum levels or major levels. And this tool can be utilized for resharpening many times. By this, the efficiency of this HSS tools, the range is gradually enhanced by improving its properties and surface conditions, such as refinement of its microstructure, addition of this large amount of this cobalt and vanadium to increase the hot hardness and work resistance nominally, manufactured by powder metallurgical processes, surface coatings in order to get the resistance material such as over this heat and work resistance such as titanium carbide or titanium nitride, etc. by chemical vapor deposition and physical vapor deposition. Nominally, the primary cutting tool materials are used for different grades, the commonly used grades of this HSS with a combination percentages utilized for different machining processes are listed over this tabular column. For the type 1, the carbon percentage will be 0.7, chromium 4, W 18 percentage, vanadium 1 percentage, and based on the series, the percentage will be ranging its number. Coming to the primary cutting materials, stellites, nominally calling the cast alloy of cobalt 40 to 50 percentage, chromium 27 to 32 percentage, palladium 14 to 19 percentage, and carbon 2 percentage, the maximum percentage that enter into the hypoelectric region. The stellite is a quite tough and more heat and work resistive when compared to the basic HSS material with a combination of 1841 as listed in the tabular column just we have seen before. The stellite, where it has been spelled satellite, but it's a stellite. Stellite is the correct spelling. As a cutting tool, stellite is nothing but a alloy material of the cast iron with a composition of these percentages: cobalt, chromium, palladium, and this carbon, sorry. And thus we'll be calling as a stellite. So hence, the stellite as a cutting tool material is used for only a poor grindability. We'll be having only poor grindability. And arrival of this cemented carbides or on its coating levels leads to an less work to the tool and high resistive to the temperatures which are produced at the machining conditions. Normally, there are cemented together with by a binders, and cutting speeds will be having 6 times much more high when compared to the HSS. And nominally, we can conclude that this stellite material can be utilized for high speed cutting processes, and feed rates and depth of cuts also will be varying. So the primary cutting tool materials such as sintered carbides, which will be having a combination that the straight cuts and a single carbide powder will be utilized in the composition or blending of a range of metallurgy, which has been compacted and sintered for 90 to 95% of the WC powder with respect to the cobalt composition. And towards this, the hard and water resistant towards the grains held to bind with respect to the carbon, cobalt, cobalt, which provides the high strength and a toughness to the tool. And suitable machining for this gray cast iron, brass, and bronze, which will produce a short discontinuous chips at high cutting velocities, that is 2 to 3 times of the HSS tools. Regarding the composite carbides is used for machining over that particular steels, even the HSS steels, which is this get that particular stability upon adding 8 to 20% of a gamma phase to WC to the palladium carbide to the cobalt mixture. This phase mixture of titanium carbide or titanium nitride or thallium carbide or nickel carbide, etc., give the more diffusion resistance than the palladium carbide. Coming to the mixed carbides, titanium carbide is not only the stable material but it's very much hard than the palladium carbide, which have a quantity of 5 to 25% of titanium carbide, which is added over the palladium carbide and copper in order to uh, produce the next level or next grade, which is called the mixed carbide, for getting the high toughness. Coming to the point of the sintered carbides, gradation of cemented carbides with respect to these applications. As per the ISO standards, it has been categorized and having different ranges depending upon the different types of applications over the machining processes has been considered. Coming to the ISO standard P, the color code will be of navy blue. It is used for machining long chip formation, for formation of the long chip and for the plain carbon and even the low alloy steels. And EM, it's an yellow color formation for machining a long and short chip formation of the ferrous materials such as the stainless steels. K is a red color utilized for the machining short chipping ferrous and non-ferrous materials and non-metals like this cast iron and brass, etc. Primary cutting tools that mainly consists of this aluminum oxide in the case of the ceramics. And previously, we have gone with respect to metals, the two ferrous content of metals and non-ferrous content of metals. And now coming to the ceramics, aluminum oxide and sintered nitride. These are very much hard with respect to the high hardness content and react with respect to the workpiece. And these are utilized at the elevation of temperature at different cutting speeds, and even that is even more than that of the cemented carpets. Even this have the low heat conductivity, high compressive strength, high hardness. It shows the better advantages and limitations, such as very high hardness in the case of disadvantage, chemical stability, anti-welding capability, less diffusivity, high abrasion resistance, high melting point, low thermal conductivity, very low thermal expansion coefficient. Coming to its limitations, it is a poor toughness, poor tensile strength, full tensile resistivity, low thermal conductivity, less density. So these are the nominal disadvantages when compared to the ceramics part. And this is the graphical representations which deviates its strength and tough as per the improvement is required. But gradually from 1970 it's been decreasing because of the following restrictions. That is uninterrupted machining is required when the machining condition is being progressed over the irons and steels, particularly because those are strength, but these tools which are being released towards this sintered materials also very much high in strength, but toughness is less. So hence high feed rate is not allowed over the particularly towards the steel materials, which is having the composition of this iron. These are relatively very much having high cutting velocity and very much narrow in range, that is 200 to 300 meters per minute, requiring very grid machine tools. And coming to the advanced cutting tools, coated carpets, ceramides, cubic boron nitrates, diamonds, these are the advanced cutting tools, materials utilized for various machining processes. For tomorrow's class, we'll be shifting to the unit number 2. Thank you.